Is the following statement true? That for all integers a, b, and c, if a divides b and a divides c, then a divides b³ plus c³. Now this is very similar to the proof I did prior to this, where it's asking whether a divides b² plus c², and we found that this was in fact true. So I'm going to kind of think that this should be true as well, but let's just verify that with just one example, right? So let's take b to be, let's say 5 and 10, and then c will take us 15, right? So 5 does divide 10, 5 does divide 15. So does 5 in fact divide 10 cubed plus, oh maybe not 15 cubed. Okay, maybe not this example, it's a little tough to cube something. Okay, we'll stick with 2 for now. So 2 and 4 and 2 and 6. So does 2 in fact divide 4 cubed plus 6 cubed? Well, let's expand this out, right? This is the same as asking, does 2 divide 4 times 4 times 4 plus 6 times 6 times 6? Our goal when we're saying something divides something is, of course, factoring out and getting it so the right-hand side is a multiple of what's on the left-hand side. So can we factor out a 2 here? And the answer is yes, we can. So this is the same as asking 2 multiplied by 2 times 4 times 4 plus 3 times 6 times 6. So this is in fact looking like it's going to be true because this fits our definition of divisibility. Again, if you're not sure what I'm talking about, watch my previous videos. Just to be even more explicit with our example, let's just verify what 4 cubed is going to be. 4 cubed is going to be 4 times 4, which is 16. 16 times 4 is going to be 64. 64 plus 6. 6 times 6 is 36. 36 times 6 is going to be some large number that I'm going to quickly use a calculator to go compute. Okay, the answer is 216. Obviously, you don't need to compute all these in a test. This is probably more than enough for you to go off of and assume that it is in fact divisible. I'm just doing this for completeness. Don't think of hard examples. In fact, maybe I should have chosen this to be 2 so we can have 2 cubed plus 4 cubed, but I chose a hard example on myself and that's my fault. So this is the same as asking, does 2 in fact divide the sum of these, which is going to be 280, I think. Right? Plus 60 is 276, plus 4 is 280. Yeah, okay. And this is in fact true because 6 divides 28, or sorry, 2 does divide 28, and this is just times 10. Or more simply, this ends with a 0, and any digit ending with a 0 is going to be even, and all even integers are divisible by 2 by definition of even. So yep, this is true. 280 can be written as a multiple of 2 because that's the same as asking 280 is equal to 2 times 140. So there we go. It is a multiple of 2 where 2 can be multiplied by some sort of integer, which means that 140 should be what this bracket is equal to. So 4 times 4 is 16 times 2 is 32 plus 6 times 6 is going to be 36 times 3, which is going to be 72 plus 6. 72 plus 6 is going to be 102? 108, I think. Yeah, that looks right. Okay. So it's looking like that this is in fact true because these do add up to 140. So this statement does appear to be true. Okay, so the first thing we should recognize is that this is a for all proof. So how do we start all of our for all proofs? We say, let a, b, and c be integers such that a divides b and a divides c and a cannot be 0. If you're not sure why I added this not equal to 0, watch my previous divisibility proofs, specifically the one where I prove that a does divide a multiple of a. Specifically that one, or if you don't like that one, a divides b plus c. Both of those are perfectly fine videos with explanations for this problem. Anyways, fantastic. Now we should probably mathematically explain what it means for a to divide b and a to divide c. Well, what it means is we can then say, then b is a multiple of a, or b can be written as a multiplied by some integer m, And similarly for c, this means c is a multiple of a, or c can be written as a multiplied by some sort of integer n, where m and n are integers. We have to explicitly state that because we've created new variables. Fantastic. Okay, what do we do next? Well, we've supposed everything. Now we can try and check if what's on the right-hand side can be written as a multiple of a, or a multiplied by something in a huge bracket, where whatever is in this bracket is going to be an integer. So let's go ahead and give that a shot. So we could say, next, 𝑏³ plus 𝑐³ is going to equal to am³ plus an³. So I don't see a way to factor out an a yet, so maybe we just expand these brackets. So this is the same as saying a³ m³ plus a³ n³. Now from here, you can absolutely factor out an a, right? This is the same as saying a multiplied by a² m³ plus a² n³. And you can argue that this is in fact an integer. I'm just going to be a little more explicit. Actually, no, I will do that, in fact. I've already done the other way I'm thinking of in the previous video with the squares. So let's go with that for this one. We could say this is the same as saying a multiplied by a² m³ plus a² n³, where a² m³ plus a² n³ is in fact an integer. Fantastic. All that's left is to write our conclusion. So we can say, in conclusion, because 𝑏³ plus 𝑐³ is equal to a multiplied by a² m³ plus a² n³, 𝑏³ plus 𝑐³ is a multiple of a, so a does divide 𝑏³ plus 𝑐³. And I'll add, by definition of divisibility. A lot of I's. Fantastic. So we have now proven that this statement is in fact true, because the right-hand side is a multiple of what's on the left-hand side.